All right. What we're going to look now is the stereochemistry involved in an E2 reaction. And there's two aspects of stereochemistry that we're going to talk about. The first of these is stereoselectivity, which is the preference or forming one stereoisomer over any others. So an example of this would be if we do an E2 elimination on this alkyl halide. Now, pulling off a beta hydrogen on one side or the other, it's exactly the same. So our base would pull off a beta hydrogen, we form a pi bond, and kick off the leaving group. Now, the two possible stereoisomers we would get for this is the trans isomer, and it would be possible also to get the cis isomer. Now, this reaction prefers forming one over the other. And in this case, since trans is more stable, this would be our major product, and this cis isomer would be the minor product. So when it comes to the possibility of forming cis or trans isomers, the trans one is going to be more stable and therefore be the product that's formed preferentially. Now, again, I don't expect you to know or even tell me what the percentages are. You just need to be able to say, well, this one's going to be the major and the other one will be the minor product. Now, here's kind of an interesting case. So I want you to copy down this structure. Now, as a side note here, you'll see there's this kind of new indication. I don't think we have talked about pH before. pH means phenyl group, which is just a benzene ring. So pH stands for phenyl, Phenyl, not the spice, but completely different phenyl there. Now, what is interesting about this reaction is when an E2 is performed on it, there is not a mixture of cis and trans isomers. The only stereoisomer that is obtained is this one, where the phenyl group ends up cis to the hydrogen, and the methyl ends up cis to the terbutyl group, not the other way around. That's the only stereoisomer that is formed. And here is the reason for this. And I'm going to kind of explain something. I don't know if you caught on to this, but there's always been a reason why I've drawn an E2 in a specific direction, where I've always pulled off a particular hydrogen in a certain way relative to the leaving group. But the hydrogen that is pulled off on the beta hydrogen must be what's called anti-periplanar. It's a fancy way for saying if the hydrogen's going one way, the leaving group has to be going the opposite way. So here this hydrogen is like straight up, this leaving group is straight down. The reason for that is since those two sp3 orbitals are in perfect alignment to form overlapping p orbitals during the process of the reaction, that's like the optimum position for a very quick E2 reaction. And so if the hydrogen that you're trying to pull off is not anti-periplanar to the leaving group, that's a very, very, very slow to almost doesn't happen at all E2 reaction. So the ideal situation is to have the hydrogen and the bromine going in opposite directions. So the beta hydrogen that you're intending to pull off and the leaving group must be anti-periplanar. So this presents kind of an interesting and kind of complicates E2 a little bit. But what do I do, or what happens? What if the beta hydrogen and the leaving group aren't anti-periplanar? So I'm going to take a very similar um, compound as to what I used here in this example. But instead of having the hydrogen going straight down, I give it this um, dashed wedge here. Okay, so this hydrogen is not anti-periplanar. So does that mean I can't do this reaction? Absolutely not. You can do it. You just have to start rotating this carbon-carbon bond around. We're going to spin this carbon bond around. And let me show you how to do that without, your textbook will have you go in to make a Newman projection and then convert that back to a skeleton formula. Here's kind of an easy way to do this. I want this hydrogen to be down here so that it is anti-periplanar to the bromine. I want both the hydrogen and the bromine to have a regular solid line to them. So I'm going to rotate the hydrogen down to where the pH is. The pH or the phenyl group will go up here to the methyl, and then the methyl will go here to the hydrogen. So all I've done is rotate that carbon-carbon bond. And so now the hydrogen has this solid line. The methyl group has the solid wedge, and the phenyl group has the dashed wedge. I didn't change the identity of the molecule. This is not a chemical reaction. This is just rotating a carbon-carbon bond, single bond. And now the hydrogen and the bromine are going in opposite directions. So all I have to do now is take my base, pull off this beta hydrogen on the pi bond, kick off the leaving group. And now here's the tricky part. How do I arrange the remaining four groups around this carbon-carbon double bond? Well, which things have the dashed wedge to them? Well, that's the phenyl group and the tert-butyl group. Since they have the same wedge, I'm going to put them cis to each other. And what things have the solid wedge? Well, that would be the methyl, and that would be this hydrogen here. And so I put them cis to each other. Remember that in these sp2 hybridized carbons, don't use the wedges. Okay, you'll probably get a little frustrated if I take off, quarter point, half a point, if you start putting wedges like this, okay, on your answers. It doesn't work like that. These are planar. Remember, sp2 atoms are trigonal planar, and so they don't have those wedges. Okay, so this is going to be an important skill. We're going to practice this in a little bit, um, because if you can rotate a carbon-carbon bond to make the beta hydrogen in the leaving group anti-periplanar, then you want to do that. So you got to be able to develop that skill. Now, the other aspect of stereochemistry is something known as stereospecificity. So think of stereoselective as you start with one particular, one compound or stereoisomer. And out of that, you get one stereoisomer over another, a preference for one stereoisomer over another one. That's stereoselective. Stereospecific is what we just did on this page here. Notice that when you compare, I want you to compare this to this. Take a look at it real quick. What is the relationship between those two compounds? If you look at it, I flipped two groups around one carbon, but I have two chiral carbons there. So those are diastereomers. So depending on which stereoisomer I start with, I get a different stereoisomer as a product. So notice the difference between these two products. They are not the same product. They are different stereoisomers of products. And that's what stereospecificity says, is depending on which stereoisomer I start with, I'll get a different stereoisomer as a product. So let's take a look at some more problems here. And we're going to assume this is going to go through an E2 mechanism. A little bit later, once we kind of complete substitution and complete elimination, we're going to put all this together. And you'll be able to look at a reaction and predict what mechanism it should undergo. But right now, let's just assume we're going to do an E2. And we're going to look here and first of all, identify where our beta hydrogens are. So here's the carbon with the leaving group. This carbon over here, this is a beta carbon, but it doesn't have any beta hydrogens on it. It's got carbons on it. So that means this one over here has a couple beta hydrogens. So I'm going to pull one of those off. Now, based off of what I said earlier, which one do you think I should pull off? I'm going to pull the one off that's going the opposite direction to the leaving group. So that's this one here. So I'm going to pull this off, do my E2. And I'm going to get this double bond, which is the trans isomer. And I'll probably get a little bit of the cis isomer as well. But this is going to be my major product. This will be my minor product. Now I'm going to change this up ever so slightly. Okay, I'm going to use this same substrate, but maybe not. I'm going to change it just a little bit and have this be a methyl group here. And I'll even draw in to help out the hydrogen. Okay, so now what I want you to look at is, do I have a hydrogen, a beta hydrogen that's anti-periplanar to the leaving group? Well, my chlorine here is going, has a solid wedge. This hydrogen does not. That's not anti-periplanar. So I need to start doing some rotating. The best way to handle these is you want both the leaving group and the beta hydrogen you're pulling off to have a regular bond, a solid line. Not a wedge, but just a regular solid line bond to them. So I'm gonna have to do some rotating here. So I'm gonna draw in the hydrogen over here. So again, if you want to set up a Newman projection and do some rotating, you can. It's a little bit easier in my opinion. I want the chlorine to have the solid bond. So I'm going to put the chlorine there where that tert-butyl group is. The tert-butyl group is going to be down here where the hydrogen was, and the hydrogen will be here where the chlorine was. So I'm just doing that side first. So now my chlorine is here. My tert-butyl group has the dashed wedge, and the hydrogen has the solid wedge. And this didn't change over here at all. But I want that hydrogen, this one here, I need to have that have a solid bond. So I'm going to do the same thing. I'm going to rotate this down here. We'll use a different color. This hydrogen will rotate here. The CH3 will rotate to where the H was. And then that other CH3, I'm sorry, that should be an ethyl group. That ethyl group will move to where the CH3 is. So let's draw the result of rotating that bond. So now my hydrogen has the solid line. The methyl has a solid wedge, and this ethyl group has a dashed wedge. And actually, just to make it a little bit simpler, I'm going to say ET for ethyl. Now that my hydrogen or I should say the beta hydrogen I want to pull off and the leaving group both have a solid line to them, I'm going to do the E2 now. So here comes my base, pull the hydrogen off, form the pi bond, kick off the leaving group. So now how do I draw this product? Well, draw your double bond, just start there. And if whatever groups have the dashed wedges, you're going to make them cis to each other. So my tert-butyl group will be cis to the ethyl group. And this hydrogen will be cis to the methyl group. All right, so again, the key thing with doing these stereo specific E2 eliminations is making sure that the hydrogen you're pulling off is going in an opposite direction. It's anti-periplanar to the leaving group. And if it's not, you have to do some rotating. Sometimes that might require you to rotate one carbon. Sometimes it might require you to rotate both. Now, the last thing I want to highlight before we do a few more practice problems is dealing with E2 and when your leaving group is on a cyclohexane ring. Okay, so again, we're just assuming we're doing E2 here. Now, if I look at this chlorine, and remember that with cyclohexane, I'm not going to draw the chair conformations, but remember that the axial and equatorial positions, the up and down, are not exactly the same. So for these beta hydrogens, I'm going to draw all four of them in. Normally we wouldn't care because you can rotate a carbon-carbon bond, but here it does matter because we cannot rotate these carbon-carbon bonds. And so technically, I have four beta hydrogens. So I got the solid ones there and the dashed ones there. Only two of these beta hydrogens can participate in the E2 reaction. I want you to take what we just learned about um, the stereoselectivity and stereospecificity. Which two do you think can be the ones that are able to be removed by that base? It's going to be the ones that are anti-periplanar, going the opposite direction to the leaving group. So I could have pulled off that one with that dashed wedge, or I could have pulled off the one on the other side. It doesn't matter which one, I would have gotten the same product. But when it comes to cyclohexane, I can't just pull off any beta hydrogen. I need to make sure that the beta hydrogen I pull off is anti-periplanar to the leaving group. And here's where this really comes into play. Now I'm going to kind of put the cart before the horse and say that the major product, actually the only product that is obtained in this reaction, is this product. The Hoffman product, the less stable alkene, is the only product. I don't obtain the Zystev product. It's not even formed in a small amount. It's not formed at all. So I want you to go back and look at the reactant, look at the cyclohexane, and I want you to maybe pause the video and come up with an explanation why the Hoffman product is the only product that is obtained and why the Zystev product is not even possible. So let me redraw this by drawing in all of the possible beta hydrogens. Now, do you kind of see why a base would not be able to deprotonate this hydrogen? It's not anti-periplanar to the chlorine, to the leaving group. The only one that's anti-periplanar is this hydrogen here. That hydrogen has a dashed wedge. And so that's the only one that is anti-periplanar in the proper orientation to pull off or to be removed by a base. All right, so let's look at the approach to predicting the product of an E2. There are some examples that are much, much easier than others. It just depends on the complexity of the substrate. Okay, so how do we approach an E2 problem? Step number one, find all of your beta hydrogens. Okay, so I'm going to redraw this problem, or at least just the substrate, and I'm going to specify where my beta hydrogens are. So here's the carbon with the leaving group. I have a few beta hydrogens over here. They're all the same, so I'm just going to draw one in. And then I have one over here. Notice that it's on a chiral center. So I'm going to be sure to draw it in with the solid wedge there. Okay, so that's step one. Step two, ask yourself, is the base bulky? Is it sterically hindered? In this case, our base here is not on our list of bulky bases. Ethoxide, even though it's got a 2-carbon chain, that's still considered somewhat small. So we know that the major product should be a Zystev product, a more substituted alkene. Now, does that mean the less substituted alkene, the Hoffman product's not formed? No, it'll still be formed just in a small amount. This will be one of our minor products. Our minor product will be a Hoffman elimination, where the base would go after this hydrogen. And we get the Hoffman product, which would be the minor one. So let's draw that up here because we've discovered one of our products, albeit it is the minor one. So this is our minor product. Do I need to worry about cis or trans? Not with this product, because there's no way, since I have two of the same group on one side, there can't be cis or trans isomers possible. Now, the more difficult part to this is, what does our Zystev product look like? And this is where you ask yourself another question. Are the beta hydrogen and the leaving group anti-periplanar? So again, I'm going to draw the substrate here. Here's our bromine. Here's our beta hydrogen right there. So I need to pull this hydrogen off. Are the bromine and that beta hydrogen anti-periplanar? No, they're not. They're not going in opposite directions. So I need to do some rotating. Okay. And again, the best tactic is to rotate until both groups, the beta hydrogen and the bromine, or the leaving group, I should say, have a solid line. So that means this bromine, I'm going to rotate this side first. That bromine will become a solid line. This, whatever this group is, that methyl group will become the dashed one, and then this hydrogen will move to where the bromine is. So what does that side now look like? So now this is my bromine. Now the methyl group is here. And now this hydrogen is here. Okay, so let's do this on the other side now. Again, I want this hydrogen to have a solid line. So I'm going to rotate it. Okay, well, now the hydrogen will move here. The methyl will move here to become a solid wedge. And this ethyl will move down here to become a dashed wedge. So now the hydrogen has a regular bond. The methyl group has the solid wedge now. And then the ethyl group, I'm just going to put ET, so that just to kind of keep it nice and neat, has the dashed wedge. Now the hydrogen I want to pull off is anti-periplanar to the bromine. It's going in the opposite direction. So I can take my base now, pull off the hydrogen, form the pi bond, kick off the leaving group. Now, what do my groups around the carbon-carbon double bond look like? Well, if they had the solid wedge, then I need to draw them cis to each other. If they had the dashed wedge, I'm going to draw them cis to each other. So the solid wedges are cis to each other, the dashed wedges are cis to each other. And so that's going to be my major product. Okay, so let's put that over here. So my major product will look like this. And I'm not going to get the other stereoisomer. I'm only going to get that one where the methyl groups are trans to each other and the ethyl and the hydrogen are trans to each other. I will not get the opposite stereoisomer because this is the only one that results when the hydrogen and the bromine are anti-periplanar to each other. So I recommend um, going through problems like this on the problem set, find examples in your textbook or online, because this is like as complicated as it gets when it comes to elimination, is dealing with the stereospecificity of the E2 reaction.